Hey everyone, in this video we're going to look at binomial random variables. Binomial random variables are based on a simpler random variable called a Bernoulli random variable or a Bernoulli trial. So a single Bernoulli trial is a random event that only has two possible outcomes, and we call these outcomes success and failure, although they don't actually have to represent any kind of real-world success and failure. Those are just labels we give to kind of an A or B type outcome. The probability of the success outcome is denoted as P, and because there are only two possible outcomes, a failure would have the probability 1 minus P, since this is the complement. The classic example of a Bernoulli trial is flipping a coin. So we could call heads a success and tails a failure. The P here would be 0.5 since the probability of heads is 0.5, and the probability of tails would also be 0.5. Another example of a Bernoulli trial or a Bernoulli random variable would be taking a randomly selected adult in the US and asking if they use TikTok. We'll call here yes a success and no a failure. The probability of success in this case would be about 0.33. This is based on a Pew Research Center survey that indicated that about 33% of US adults use TikTok. So the probability of any given person saying yes here is based on that kind of empirical result. So while these Bernoulli trials or Bernoulli random variables are looking at just two possible outcomes, a binomial random variable is based on that, but adding up the number of successes that we get in a repeated number of trials of Bernoulli type outcomes. So our binomial random variable has a few different criteria. One is that we want a fixed number of trials. So whatever Bernoulli trial we're doing with the success and failure outcomes, we're doing that a fixed number of times, and that number is called n. Each trial needs to be independent of the others. Each trial has only two outcomes, success and failure, which is part of being a Bernoulli trial. And the probability of success, which we're still calling P here, that needs to stay the same for every trial. So that's not going to vary over time or based on the success of trials. And the random variable here is not just a yes or no, but rather the number of successes that we see in this group. So here are some examples. We could have the random variable, the number of heads in 10 coin flips. So that number is the number somewhere between 0 and 10. And it's based up on adding up the number of successes or heads within those repeated trials. In this case, the repeated trials would be flipping the coin over and over. Another example would be the number of defective products in 20 chosen from an assembly line. So the 20 different products being chosen, those are those repeated trials, and here would be 20. And each one of these products that's chosen is either defective or it's not defective. The defectiveness would be what we would call success in this case. So again, success doesn't have to be necessarily a qualitatively positive thing. It's just denoting whatever outcome we're counting. A final one related to the Bernoulli trial example from before is the number of TikTok users in a random sample of 10 adults in the US. So here again, we're counting the number of yes answers or the number of successes finding someone who uses TikTok when we talk to 10 randomly selected adults. Now, the criteria of independence does require that in the second and third examples here, when we're selecting these 20 parts off of the assembly line or selecting the 10 adults from the US, that selection is supposed to be with replacement to guarantee probabilistic independence. That might not always be the case, but as long as we're selecting a small number from a larger population, 10 adults out of all of the adults in the US is a very small proportion, or 20 products from an assembly line. I'm assuming that this assembly line has hundreds or thousands of products coming out. So even though these might not technically be with replacement, we can probably still treat them as independent events. A Few examples that are not binomial. So if we looked at rolling a six-sided die 10 different times and then adding up the sum of all of those rolls, this is not binomial because the different independent trials rolling the dice don't result in one possible or two possible outcomes. This is not a success and failure. This would be 6 possible outcomes for each of those trials. The second non-example here is the number of siblings in a family of 4 children who test positive for a genetic disorder. We do have a fixed number of trials here. We're testing each of the 4 children. The outcomes of each of those trials are also either a success or a failure. Either they test positive or they don't. But these events are not independent. So because these are children from the same family, if one tests positive for a genetic disorder, that means that the other children are more likely to test positive as well. They're not independent unless these were selected from kind of a wider population or we were testing for something that wasn't genetic. And the last non-example here, the number of registered independents in a group of 100 voters. So here again, we do have a fixed number of trials. Those are the 100 voters. We're looking at the probability that each one is independent, which should be the same probability in all of our trials. The issue here is that there seem to be more than 2 possible outcomes here. And this last non-example would kind of depend upon how you're coding the results. If you're recording what political party each voter belonged to, that's going to be more than 2 possible outcomes. We can have independents, Democrats, Republicans, or potentially other political parties as well. You could make this binomial, though, as long as we were just saying success is getting an independent and failure is getting anything else. So you could modify this last one to be binomial, but we do need those 2 success and failure outcomes to be a binomial situation. When we do have a random variable that satisfies these binomial criteria, the probability of any particular value of that binomial random variable is given by this binomial probability formula. So I have the algebraic formula here, as well as how we'll do this in Excel. So the algebraic formula begins with this notation here, n over x in parentheses. This is n choose x, or the actual formula for this looks like n factorial divided by x factorial times n minus x factorial. You may have seen this before in the counting section, but if you haven't, don't worry about it. We don't have to use this formula to calculate the binomial probabilities. Excel can also do this for us, as well as other technology like graphing calculators or an online calculator. But you'll see that in either case, the probability calculation depends upon the number of trials, that's our n, as well as the probability of success on any given trial, that's p, and then how many successes are we looking at, that would be our x value. So let's look at an example. According to an article by Sandra Guerra Thompson in the UC Davis Law Review, scientific evidence indicates that eyewitnesses attempting to identify a stranger in a criminal lineup identify the wrong person about 20% of the time. So we are looking at the question of, if we looked at 50 different criminal lineups, how many of those criminal lineups would result in wrongful accusations? So on average, that's going to be 20% of them. We could find 20% of 50, but this is actually a binomial random variable because in any one of these criminal lineups, the eyewitness might identify the wrong person or they might not. There are 2 possible outcomes, and that is going to be random, where the probability of identifying the wrong person, or the probability of, we'll call this a success, is 20%. So in this example, the trials would be each individual criminal lineup. N is 50 here, we have 50 trials. A success would be on any given lineup, we want to know, does the eyewitness identify the wrong person? And again, getting the wrong person in a lineup is not a good thing. We're not calling this a success in the wider context, but the reason we identify this outcome as a success is because this is what we want to count. How many of these lineups end up in a wrongful accusation? So our random variable x is going to be the number of successes. In this case, it's the number of wrongful identifications in these 50 lineups, in the 50 trials. The probability of success based on that data from the law review article is 0.2. So say I wanted to know what is the probability of seeing 8 wrongful accusations within the 50 criminal lineups. This is the probability that x equals 8, that our number of successes is 8. If we did this with the algebraic formula, it would look something like this, but I'm going to calculate this in Excel. So I'm just going to go to an empty cell, I'll do equals, and I'm using BINOM.DIST. This stands for binomial distribution, and then I'm going to do parentheses to start. You'll see that in Excel, it tells me the first input here is number underscore s. That stands for number of successes. This is my x value. In this particular case, this is 8 because I want to know what is the probability of 8 successes, comma. Now I have trials. This is the number of trials, or the n value. That was 50 in this example. And then the next input Excel is telling me is probability underscore s, or probability of success. That is the p-value, which was 0.2 in this problem. The last input to this function is what's called a flag. This is the cumulative flag. There are 2 different versions of the binomial distribution formula. One is a cumulative probability, and the other one is just a non-cumulative. We want the non-cumulative probability here. I'm going to put false in this last input because I want just the probability of 8. If you do the cumulative version, so if I put true here, it will find the probability of 8 and less. So it's that number and everything below. You can certainly use that version of the function in some cases, but really you can do all of your binomial probability calculations with this non-cumulative version. So we can just put false in the last input. Just so that you're aware, false is the same thing as 0 in Excel. So if you want, you can just put 0 here. Excel will interpret it the same way, but I'm going to put false. So this number that it spits out, this represents the probability of 8 of those 50 criminal lineups resulting in wrongful accusations, or about 11.5% likelihood. Another example, same scenario, what would be the probability that all 50 lineups would result in wrongful accusations? So here we're looking at the probability that x equals 50, or that every single one of these lineups would result in wrongful accusations. If you compute the algebraic version of this formula, you'll find that this is actually just 0.2 to the 50th, because the probability of any one of these lineups resulting in a wrongful accusation is 0.2, and this is essentially just an and probability. It's 0.2 times 0.2 times 0.2 times 0.2 50 different times. You could compute this on a calculator or in Excel, or we can use our binomial distribution formula again. The only thing that's going to change is that instead of looking at 8 successes, I'm looking at 50 successes. And you'll see that this number in Excel is giving us a scientific notation result. This minus 35 represents 10 to the minus 35 power. So this is really equivalent to 1.1259 times 10 to the negative 35th. This means that we really want to move the decimal place in this decimal 35 places to the left. This is an incredibly small number. If I convert this, if I go to the Home tab and go into the number formatting, I can turn this into just a number, and you'll see that this is a decimal with just a ton of zeros. If you go far enough, it'll probably show us a number. Yeah, here it is way down here, but 34 zeros and then 11259. Obviously, it's very unlikely that all 50 lineups would end up in wrongful accusations, because the probability of a wrongful accusation is only 20%. Often when you're working with a random variable or a binomial random variable, we'd like to just create a probability distribution table. So for 50 trials, and if we're tracking this number of incorrect identifications, I can create a table that tells me the probability of any of the possible outcomes. So I'm going to make a table with x and p of x here. My x column is all the possible outcomes for this random variable, which in this case is going to be the numbers 1 through 50. I'm going to type in here 0, 1, 2, 3, 4, and rather than having to type all of these numbers, if I highlight this range and then grab the bottom right-hand corner, Excel will continue this pattern, and I can just drag this all the way down until I get to 50. That would be in row 52 here. So now I have all the numbers from 0 to 50. Now, this is 51 different probabilities, but they're all using the exact same function. So I'm going to compute the probability of 0 here with the BINOM.DIST, BINOM.DIST, parentheses. My number of successes is the x value. In this case, I'm looking at the number 0, but I'm going to click on that x value in the column on the left, comma. The number of trials is 50 in every case. The probability of success is 0.2 in every case. And I'm using the false or the non-cumulative version of this probability. So here we see the probability that none of the 50 criminal lineups have false accusations. Again, a fairly small number here. And then I'm just going to drag this down by clicking that bottom right-hand corner. I want to use the same formula for all of these different x values. The only thing that's being updated in this case is the number of successes, or that x value in the left-hand column. So now I can look into this table. That previous question about the probability of 8, I could look this up right from the table. I could also find ranges of probabilities, like what's the probability that 10 or fewer of the lineups would have false accusations. I can look at the possibilities of 10 and below and just add up these numbers with a sum. In this case, I'm seeing about 58% chance of 10 or fewer false accusations. So creating these tables can be really handy, especially if you're answering a lot of questions about probabilities. One last thing I want to mention about binomial random variables is that we do actually have some special kind of shortcut calculation or formulas for computing the mean and the standard deviation. So if we know that a random variable is binomial, rather than doing the longer table calculation for mean and standard deviation, you can use these two formulas. So for this example, the mean would be just n times p. N here was 50 times p was 0.2. The mean, or the expected value, the number of criminal lineups in 50 that we would expect to have wrongful accusations, is 10. This is literally just 20% of 50. And then the standard deviation would be the square root. So in Excel, this is equals SQRT. You could also do this on a calculator, of n, 50, times p, 0.2, times 1 minus p. That's the probability of a failure. I could just put 0.8 here, or if I want to calculate this in Excel, I'll do some parentheses and then 1 minus 0.2. Close my parentheses for the 1 minus 0.2, and then close my parentheses again for the square root. This gives me 2.828. So on average, there will be 10 mistakes or misidentifications within this group of 50 lineups, and that number is going to vary on average by about 3. So this gives us a good sense of kind of what the typical range of outcomes would be, somewhere around 10, with less likelihood of the higher numbers or the lower numbers in that distribution. That's it for this video. Thank you for watching.